So in this video we're going to provide a justification for the directional derivative formula, and the justification is going to involve the chain rule and a little bit of algebra. So in video 1 we developed the equation for the directional derivative in the direction of u hat. And what we discovered was that we could calculate that directional derivative by taking the limit as t goes to 0 of this difference quotient that's right here. So this is just the formula we developed in video 1. And then we claimed that there was a shortcut formula that would allow us to calculate the directional derivative without having to take the difference quotient, the limit of the difference quotient as the denominator, or t went to 0. So what we want to recall is in video 1 we parameterized x and y. So we had our function f for which we were interested in finding a directional derivative, and we parameterized x and y as x equals x naught plus t times u sub 1, which is why that's showing up here. And we parameterized y as y naught plus t times u sub 2, which is why the y naught plus t times u sub 2 is showing up in the y position in our function f. And when we replace the x and the y with their parameterized versions like we do here, right, when we replace x and y with the parameterized versions, what we recognize is we really have a function of t. So we'll call it g of t equals f of xy equals f of, here's the parameterized versions of x and y. So g of t and f of x are the same function. And then what we want to recognize is that if t is equal to 0, so if we plug 0 in for t, these are going to die, and we're just going to get f of x naught comma y naught. So g of 0 equals f of x naught y naught. So when we look at the difference quotient, where we took the limit as t goes to 0 from video 1, what we recognize now is because g of t equals f of xy, we can replace the f of x naught y naught with g of 0, because g of 0 is the same thing as f of x naught y naught, and we can replace this mess here with g of t because we gave this parameterized function f the name g of t. So making those replacements right here, I get a difference quotient, g of t minus g of 0 over t, the limit of a difference quotient as the denominator, or t goes to 0. And we want to recognize that when we take the limit as the denominator goes to 0 on a difference quotient, we're calculating a derivative. But when we put a specific value in for t, we're calculating the derivative at that specific value. But the bottom line is that this tells us that the directional derivative in the direction of u is the same as g prime of 0, where g is just the parameterized function of x and y. So this is important to us because if we want to know the derivative of g with respect to t, because g of t equals the parameterized function f of xy, we would need to use the chain rule to calculate the derivative of g. We would need to do partial f, partial x, the rate of change of the function f because of changing x, but then we would have to recognize that because x is changing as a function of t, we need to multiply by dx dt to get the change in f as a function of change in t because of x. And then we need to add to that partial f, partial y, but y is changing as t changes, so we have to multiply by dy dt to get the change in f with respect to t that happens because of changing things in the y direction. And then if we just use the notation we've been using, we can replace the partial derivative, partial f, partial x, with f sub x. Partial f, partial y means the same as f sub y, the partial derivative with respect to y. So this is the derivative of g, right? So, and that's replaced here. So if we want the derivative of g, we have to do this calculation. But The directional derivative is the derivative of g at a specific value. So if we replace t with 0, what are we going to get? Well, when we replace t with 0, we already know right here we're going to get y naught, and when t is 0, we just get x naught. So the x and the y get replaced with x naught, y naught when t is equal to 0. The x and y get replaced with x naught, y naught when t is equal to 0. And dx dt, what is dx dt? So if we look up here, dx dt, when we take the derivative of this, because x naught's a constant and u sub 1 is going to be a constant, the derivative is just u sub 1. And so dx dt is u sub 1, and right here dy dt, well, y naught's a constant, so its derivative is 0. U sub 2 is a constant, so u sub 2 times t, when we take the derivative of y with respect to t, we're just going to get u sub 2. So dy dt gets replaced with u sub 2, and then that gives us a justification for using the shortcut formula for calculating the directional derivative without having to actually do the difference quotient definition for it.